partial differentiation. Let us consider a rectangle with area A such that it is proportional to the length L and breadth B. That means that area is a function of two variables, the length and the breadth. Symbolically, we can write this as A is a function of L and B. In general, let Z be a function of two variables, X and Y. Z is going to have one definite value for every pair of X and Y. Or we can say Z is equals to f of X comma Y, or function of X and Y. Geometrically, X and Y belongs to an area A of the XY plane. Now each point X comma Y corresponds to a value of Z. The values X, Y, Z form a surface and space. Z equals to f of X comma Y represents a surface. Limit. The function f of X and Y is said to tend to the limit L as X approaches A, Y approaches B if and only if the limit L is independent of the path followed by the point X comma Y as X approaches A and Y approaches B. So we have limit X approaching A and Y approaching B, f of X comma Y is equals to L. Delta definition. The function f of X and Y in region R is said to tend to the limit L as X approaches A and Y approaches B if and only if, corresponding to a positive number epsilon, there exists another positive number delta, such that the absolute value of the difference of the limit L from the function is always less than some positive number epsilon, for x minus a squared plus y minus b squared is less than delta squared for every point x comma y in the region R. Working rule to find the limit. Step number 1, we are going to determine the value of the function f of x and y. First, along the path x as it approaches A, followed by along the path y as it approaches B. Step number 2, then we are going to determine the value of x and y along the path y as it approaches B, followed by the path x as it approaches A. Then we are going to check that the limiting value of the function x comma y as x approaches A, followed by y approaching B, it must be equals to limiting value of the as y approaches B, followed by x approaching A. Then this limit is going to exist, else not. The value of the function somewhere near the origin, so that means when a comma b approaches the point 0 comma 0. In number 1, we begin by finding the limiting value of the function f of x comma y as x approaches 0, and then the limiting value when y approaches 0, and let it be the function f of 1. Next, in number 2, we are going to determine the limiting value of the function f of x comma y as y approaches 0, followed by the limiting value when x approaches 0, and let this be the function f2. Then we are going to check that whether they are equal or not. If f1 is not equals to f2, then the limit doesn't exist. We will stop there. However, if f1 is equals to f2, then we will have to go a step further and then put y equals to mx and determine a new function f3. If f1 is equals to f2, which we have already proved, but it is not equals to f3, then the limit doesn't exist. On the other hand, if f1 is equals to f2 is equals to f3, then again we have to replace y with a new value, which is mx squared, and determine another function f4. And then we're going to check f1 is equals to f2 is equals to f3, and if this is not equals to f4, then limit doesn't exist, and if it is equals to f4, then limit is going to exist. Now we will try to apply this particular working rule to compute the value of certain limits. So let's try it out. Problem number 1. Show that for the function given by for f of x comma y equals to x plus y divided by 2x minus y, the limit doesn't exist when x approaches 0 and y approaches 0. So here we have to apply rule number 3 because the points x and y are approaching the origin. So we first begin by calculating the limiting value of the function when x approaches 0 followed by y approaching 0. So this gives us 0 plus y divided by 2 times 0 minus y. Here we have replaced the value of x with 0 and that leaves us with y over negative y, which is negative 1. And finally applying the limiting value of y, limiting value as y approaches 0, so that is going to give us negative 1. Then the other way around, we determine the limiting value of the function as y approaches 0 followed by x approaching 0. To do that, we are going to replace the value of y with 0 into the given function. So that gives us x plus 0 divided by 2x minus 0, which leaves us with x over 2x. The x and x gets factored out, leaving us with half. So we have limit x approaching 0 of half, which is half. Now clearly we see that the two limit values are not equal. So we can say that the limit doesn't exist when x approaches 0 and y approaches. Problem number 2. So we need to find the limiting value of the function given by x squared times y divided by x raised to the power of 4 plus y squared when x approaches 0 and y approaches 0. So here we need to apply rule number 3. So we first begin by computing the limiting value of this given function as x approaches 0 followed by the limiting value when y approaches 0. So to do that, we're going to replace the value of x with 0, which leaves us with 0 squared times y divided by 0 raised to the power of 4 plus y squared. And that is giving us 0. So we need to find out the limiting value of 0 when y approaches 0, which is equals to 0. And let us term it as f1, suppose. Now we determine the limiting value of the function as y approaches 0 first, followed by x approaching 0. So for that we are now going to replace the value y with 0. So that will be x squared times 0 divided by x raised to the power of 4 plus 0 squared, which is going to give us 0, and limiting value of 0 as x approaches 0 is also 0. Let this be f2. Now since f1 is equals to f2, we need to go a step further and we have to suppose that y is equals to mx, such that f of x comma y now becomes x squared times, in replacing y with m times x, so that will be mx divided by x raised to the power of 4 plus mx whole squared plus mx squared, which gives us mx cubed divided by x raised to the power of 4 plus m squared x squared. Now we factored out x squared from both the numerator and the denominator, which leaves us with mx divided by x squared plus m squared. Now this is the new function, so we begin by the limiting value of this particular function as x approaches 0 followed by y approaches 0. So we substitute the value for x and y, and that gives us 0, and let this be function f3. So clearly we're seeing that f1 is equals to f2 is equals to f3. So we again have to go one more step further and then assume that y is equals to mx squared, such that now we have to replace the value of y with mx squared in the original function. So that will give us x squared times mx squared divided by x raised to the power of 4 plus y squared. So y will get replaced by mx squared. So mx squared squared. This gives us mx raised to the power of 4 in the numerator divided by x raised to the power of 4 plus m squared x raised to the power of 4 in the denominator. So we can factor out x raised to the power numerator in the denominator, and this will make the function be m divided by 1 plus m squared. Now we calculate the limiting value of this particular function as x approaches 0 and y approaches 0. And this the value will be m over 1 plus m squared. Let this be f4. Now we see that f1 is equals to f2, which is also equals to f3, but this is not equals to the function f4. So we can say that the limit does not exist.